are online. So it'll just be a live Zoom broadcast and there won't be any recording. Anyway, we've got this enumeration of the k recomputable partial functions. It allows us to now, this is a very simple example, but it allows us to give some arguments very concisely, the kinds we had before. So I'm going to give a proposition where one of the first things we did with the Turing machine model was construct a non-computable function. I'm going to show you how easy this is given this enumeration of computable partial functions on the natural numbers. So the proposition is the following function which is a total function of the natural numbers is not computable. And this is n maps to, so I want to define total function on the natural numbers. And we're going to map to the, map n to the, let's call it h. So h is going to map n to the nth computable function applied to the argument n, and we'll add 1 to the result of that if phi of n is defined. And otherwise, we'll map to 0. Okay, so this is a very simple definition of a function. For any number, we look to see if the nth unary, so by phi of n here, I mean, so in the case that we're looking at unary functions, I shall not write the superscript 1, okay? So we mean superscript 1 for unary computable function. So in the case that the nth unary computable function applied to the argument n is defined, we return the value of that plus 1, otherwise we return 0. That's a simple it's a total function by definition, and it's not computable. And the proof that it's not computable is just really easy, which is if it were computable, then it would appear somewhere in our enumeration, and so there would be some number e that's an index for it. So if it were computable, we would have h equals phi sub e for some index e. So we think of the numerical index as a code for the partial function, in this case a total function, h is a total function, and it's explicitly defined as a representation, a numerical representation of a Turing machine computer function. But if we have h is phi sub e, we then have that h applied to e is, well, that's phi sub e applied to e, because h is phi sub e by this equality, and by the definition of h, this is also phi. Well, we have to see if phi sub e of e is defined, but phi sub e is h, and that's a total function, so it's necessarily defined, and by this definition, h of e is then phi sub e of e plus 1. And that's, of course, a contradiction because the value h of e cannot be these two different values, both these two different values. That's a contradiction. This is, as you know, I think we've had it before, my symbol for a contradiction. We get a very simple contradiction, and so that function is not computable. So actually, in a sense, you may have noticed that the argument so far is a little bit following lecture 2, doing sort of analogous things using numbers. So in lecture 2, the first thing we did was we encoded Turing machines as strings. Now we've analogously encoded computable partial functions as numbers. That was our enumeration. And once we had encoded Turing machines as strings, the first thing we did was constructed a non-computable function very similar to this. Well, actually, it was an undecidable language, but using a very similar diagonalization argument. So here, we're applying the nth function to itself. So that's a sort of diagonalization argument. So this is analogous to what we did in lecture 2 when we showed that there was a we gave an explicit example of an undecidable language. The next thing we did in lecture 2 was discussion of the universal Turing machine. We don't have Turing machines now in the model. We want to think about just computable partial functions. What we have instead of a universal Turing machine is a universal computable partial function, or actually a family of universal computable partial functions, one for each arity f. And the next thing I want to do is establish the universal computable partial function. One of the nice things about this approach is, whereas the very definition of the universal Turing machine was pretty involved, the definition of the universal computable partial function is now very simple.
Move camera, please.
Sorry, move the camera, thank you. Oh, sorry, I just need to do one more thing online just to get, so I can see what's being recorded. Well, not recorded, what the camera is doing better. Oh, come on. That's better, right. Right, so oh, hang on, still not moved. So it's funny, this this computer screen is inverting the picture mirror image, like if you're doing a selfie. So it's very confusing for the board, and obviously I could switch that around, but I just don't want to faff around with the computer more than I have to. So I'll try to get used to it. Anyway, so what the universal computable partial function is for any a greater than or equal to 1, I don't know why I put that restriction in, but anyway, define what I'm going to call the universal function. So this is psi sub u for universal, is now psi rather than phi, of arity k. And this is a k plus 1 function. So it's a partial function with k plus 1 arguments. And it simply computes the universal partial function. The idea of the universal Turing machine was, as an input, we give the universal Turing machine an encoding of a Turing machine that the universal Turing machine is going to simulate. Analogously, the universal partial function, as an input, we're going to give it a code for a partial function that the universal partial function is going to compute. So the first argument is going to be a code E for a partial function, and the remaining k arguments are going to be arguments to give that partial function. So we simply define the function, the universal partial function is defined automatically from the enumeration we have of our computable partial functions of arity k. The universal one applied to E simply evaluates the E indexed computable partial function of arity k on the inputs x1 through to xk, on the arguments x1 through to xk. And the theorem is that this is called the universal function. Notation psi sub u. And again, in cases that I don't put the k there, I mean k equals 1. That's the default case. The theorem is for any k, psi k u, the universal function of arity k plus 1. So the k universal function is computable. Okay, let's prove this. It's not a log proof. Again, we're going to see that somehow everything can be defined, the properties that we want, so that the fact that we had an enumeration of the computable partial functions, that the idea of that could be defined without reference to Turing machines, but to give the specific enumeration, we use reference to Turing machines. Again, definition of the universal computable partial function can be given now without reference to Turing machines, but to prove that it's computable, we're going to show that there exists a Turing machine that computes it. So what do we need to do? Well, the Turing machine here is going to need to input, the Turing machine that computes this is going to need to input the numbers e, x1 through to xk, and return this value here. What is e? Well, e is the index for the particular computable partial function phi sub e. And we already showed that that is defined. The index is the number encoding the string representing the Turing machine. So we want our Turing machine to take this input e, decode it as a Turing machine, and then simulate that Turing machine, applying it to the inputs x1 through to xk. So unsurprisingly, the Turing machine that does that is going to make use of the universal Turing machine. So although we've got a nice neat definition of a universal function, we still need to use our quite complicated universal Turing machine to actually show that it's computable. So we construct a Turing machine. Construct a Turing machine. For some reason I call it V. That computes psi u arity k. So the input to this Turing machine V is going to be a k tuple of binary representations of numbers. So given an input of the form binary representation of E, comma, binary representation of x1, comma, binary representation of x sub k. V proceeds as follows. So essentially what we want to do, we're given this k plus 1 tuple of inputs, we want to decode them as numbers, then take the number that we've got for E, decode that into a string representing a Turing machine, apply the universal Turing machine to that Turing machine, giving it these inputs as arguments. So the steps are: check if E is the number encoding the string encoding a Turing machine of n for some Turing machine n. So to do this, you find the unique. So we've got a number, we want to encode it firstly as a word. So we find the unique word of numbers that this number represents, because remember the encoding of words was a bijection between n star and n. So we find the unique sequence of numbers that E represents. We look to see if that sequence of numbers is indeed from over the appropriate alphabet. We then, if it is, we then look to see if it has the right format for the encoding of the Turing machine. So, it's a representation of the start state and the number of states and then the square brackets of the transition relations and this kind of stuff. And if it is, we carry on. Otherwise, if not, then go into a loop. So if not, this can be perfectly well computed, go into a loop. That we don't wrongly return end in the hold state. So if the above check succeeds, we run the universal Turing machine. So I'll just write UTM on the input. So we want to give the universal Turing machine the encoding of the Turing machine, together with the arguments we want to give the Turing machine, which are the numbers x1 through to xk in binary representation. So we keep those binary representations. So the universal Turing machine on this input will simulate the Turing machine, the effect of the Turing machine M on this input. We then wait to see if we get into a hold state. If we get into a hold state, we look to see if on the tape we've indeed left the binary encoding of a number. So if the UTM terminates in hold state, check to see if B Y, so if the tape contains the binary representation of the number, remains on the tape. This just means if some number of the formed binary representation of Y remains on the tape. If so, halt, because we've got an output, otherwise loop. Basically, this recipe does exactly what uses the universal Turing machine to simulate the way we define these phi sub E functions, as each phi sub E is the function computed by the partial function computed by the Turing machine with numerical code E. Okay, so that is the universal computable partial function. The point is, once you've seen an outline proof for why it exists, we can ignore that, and we can just then live with the existence of the function and this definition of it, which gives us all the properties we need. So somehow, sort of the moral of the lecture today is, in order to prove things work and to establish the very details of the definitions, one needs to use the Turing machine model. But once you've done that, you're left with high-level descriptions that are very simple and can then be used to show consequences. And so just like we had a very simple construction of a non-computable function earlier, I now want to give another example of a non-computable function that uses the universal Turing machine. Sorry, not the universal Turing machine, but uses the universal partial function to show that it's not computable. And this now goes beyond what we did in lecture 2. The total function below is not computable. This is going to be the function. That's again, let's see what I call it in the notes. So I call it G, doesn't really matter. So G takes the number X. And the idea is it's going to try to decide, so return a decision procedure, so return yes or no, decide if the number X represents a total computable partial function, unary partial function. So every number X represents a partial function phi sub X, the unary partial function. So remember, if I don't put the 1 there, I don't put the parity there, it's 1. So every number represents phi sub X, that's a computable partial function. The question is it total? We want to try to decide that, we want a computer to decide that, so we want it to be computable to answer the question, is it total? So we're going to return 1 if phi sub X is total, and 0 if phi sub X is not a total. So total means defined on all numbers, not total means there's at least one number on which it's not defined. It's not really surprising we can't do this. I mean, we can't even decide if it holds on a single given input, as you already found out in the last week's exercise class or something. So to decide if it holds on all inputs, which is essentially what we're doing, should be an even harder question. And so it's not surprising that we can't do it. The point is, we now have a powerful tool for establishing such things by very simple arguments. So let's just prove this. So we'll suppose the contradiction that G is computable. Let's suppose G is computable. So then, if it were, so let's consider the function, which I'm again going to call H. I'm going to have lots of functions that I call G and H in these lectures. They're always temporary names. So again, I'm going to do a sort of diagonalization thing, but H of X is going to be phi sub X of X. So the same applied the X index partial function on X to that value plus 1. But whereas now we don't do this only if phi sub X of X is defined, but we're going to do this if phi of X is a total function. In which case phi sub X is certainly defined on X, but it's also defined on all other arguments, is a total function. And otherwise we'll return 0. And the point is, H of X if we assume that G is computable, h of x is itself a computable function. And to see that, we need the universal computable function. Because G is assumed computable, H is also computable. Because we can write H in a clearly computable way. We can say that H of x is what we get by firstly doing an if then else. We check G of x and see if it's 1. We've assumed that G is computable. So if G of x is 1, then, well, that means G is the function that returns 1 if and only if phi x is total. So if Gx is 1, we want to return phi sub x of x. But we can do this computably because that's phi sub u applied to the argument xx plus 1. Okay? So we use the universal function here to be able to compute the output from the input x. Okay? This, if we didn't have the universal function, then we wouldn't have a single algorithm giving us for any x, changing the function to the appropriate phi of x for any x. We need the x as an input, and we get the function phi of x out of it because we've got the universal function. So if then else, so the else is that if g of x was 0 instead, then we return 0. Okay, so I hope you see that the fact that we've got the universal computable function plus the assumption that G is computable, it means that H is computable. But if H is computable, we're going to get a contradiction in the same way that we had a contradiction before. So let's do that. Continue here. But if H is computable, we have the same style of argument we had before. So then H is phi sub E for some E. And we get a contradiction that H of E will be and then we have phi sub E of E equals H of E equals, because H is phi of E, equals phi sub E of E plus 1. So again, the contradiction. And the symbol is that we've reached a contradiction. Okay, so I hope you see that this sort of abstraction of the idea of the universal Turing machine now to the universal computable function, computable partial function, has this sort of allows one to do these rather simple arguments just using sort of functions on natural numbers as the basic ingredients and combining them in this way using sort of simple closure properties like this of computable functions. I mean, here, essentially what we're using, well, that we can do if then else tests on Boolean results, on 1-0 results, and then some composition with functions. And this is all supported by the ways of combining computable functions that we had last week, this composition, primitive recursion, and minimization. And you're going to see ways of building up such combinations of functions like this in the exercise class today. Okay, so I want to make another comment about what we've established here. So one way of looking at this universal computable partial function, maybe I'll put it down at the bottom. So we were viewing a function that takes an index e to be computable partial function phi sub e as a representation of the k-array computable partial functions. So the equivalent statement of psi u being computable is the following. A function that takes a partial function f and a k-tuple of inputs to f and applies the partial function f to its k-tuple of arguments is computable as a function between represented sets. So what's it taking here is taking a pair, takes a computable partial function from n to the k to n, and a k-tuple of natural numbers, and it maps this to a single number f. This is the set of all k-arity computable partial functions. This is the set of all k-tuples of natural numbers, has an obvious representation generalizing the representation of pairs of natural numbers. This is the set of pairs of such things consisting of a computable k-array partial function and the k-tuple natural numbers. And we're looking at a function that takes such a partial function, takes a k-tuple of arguments, and applies the function to the k-tuple of arguments to give us a natural number. And that partial function, that's a partial function on functions and numbers, that partial function is computable in the sense that there's a computable function in the sense of computability between representations. There's a computable function on the numbers, on the number representing this data, that gives us the output. And that statement is equivalent to saying that the universal function is computable. So the universal function being computable, which one can understand in this very concrete way here, this partial function is computable. More abstractly, saying a function that performs evaluation on computable partial functions is computable. And in the same way, what this is saying is that the subset of the unary partial functions, computable partial functions, so G is a number of unary partial functions or natural numbers, consisting of total functions. So this is a subset of all partial functions, namely the total partial functions, is not decidable. We use the notion of a decidable subset of a represented set from lecture note 3. Okay, so I wanted to make these connections. There are two levels at which you can follow the course. So one is to understand the concrete statements, and there's a slightly higher level for those of you who like more abstract pictures, which is to understand the equivalent forms of the statements as what they're saying about functions or subsets on represented sets. Okay, so it's not a requirement that everybody understands the second point of view. The concrete part, I think everybody should be understanding, at least with some work at this point of the course. But the second point of view, I'll keep on coming back to this, because for those of you who like the abstract point of view, it's an elucidation of what's really going on. So here the point is, we can compute an evaluation function, we can't decide totality. That's the abstract point of view. Okay. Right. So maybe I will state the next. So now I want to go beyond this to the next thing we can do with this representation of computable partial functions. I'll state it before the break, because this is now a more convoluted statement, and then we'll look at it after the break. We'll give you a bit of time to stare at it and think about it, and then we'll look at it after the break and see what it really means. So yeah, I'm not quite sure whether everything was visible to everyone on Zoom, but we're down to 2 anyway. So, I'm sorry, but do shout if I'm not showing something. So the next statement is a very famous theorem in computability theory, again about the way we enumerate these partial functions. It has a rather funny name, the SMN theorem. It's called the SMN theorem because it establishes the existence, or it rather states the existence of functions called SMN. So this says, I'm just going to state it, and then, as I say, we'll have context after the break. So for every, I shall trust, I should think through the strict and non-strict inequalities once again every time, but I haven't actually done that today, so I shall trust that they're correct. It's certainly correct, but the question is whether it's the most general form, correct most general form. So for every n strictly greater than n, which is greater than or equal to 0, there exists an n plus 1 argument, so n plus 1 array. Its arity is n plus 1. It's a total function, and it's not just a total computable function, it even has the nice property that it's primitive recursive. So it's just defined using, it's definable using just those basic functions, composition and primitive recursion. So there's remember from last week, every primitive recursive function is total. So there's an n plus 1-ary primitive recursive function. S superscript n subscript n. So I've already said it's an n plus 1-ary function, arity function. And because it's primitive recursive, it's necessarily total, and it returns a natural number. And its property is such that s dot t dot for all e x1 through to xn, if we consider the well, let's put it, let's start with the right-hand side, but I need to leave enough space. So we can compute the computable partial function of arity m and index e, so the eth n-ary computable partial function. compute that on the arguments x1 through to xn, we can compute that by actually computing a different partial function on only some of these arguments, namely those from n plus 1 upwards. So we just consider the arguments from x plus 1 to n. So what we want to do, we want to compute the e-index n-ary function on x1 through to xn with a function that we only want to give it the last arguments for. So the idea is here, what we want to compute is an index for what's called in computer science, the partial evaluation of this function, where we fix the arguments x1 through to xn and make the function only vary in the remaining n minus n arguments. And the point is that partial evaluation can be computed by this primitive recursive function here. So the function Sm sub n, we apply that to x1 through to xn, sorry, xm. Hang on, we need to give it e as well. Xm. Did I give it e first here? Yes. Right. So this Smn computes us an index for this function when we fix the arguments x1 through to xn. Okay, rather a complicated thing to get your head around, but it's now exactly 5 o'clock, and so we will start again at exactly 5:15. Well, it's approximately 5 o'clock, and we'll start again at approximately 5:15. That's what I mean to say. And in the meantime, you can try to understand this statement, and I shall offer some more context after the break. Okay, good. Yeah, there's no recording to stop. So, are there any? Okay, so it's approximately 1:15. So let's punctually start. So I ended the last hour by stating this. Yes. Hello. Hi. So good. So I ended the last part by stating this maybe quite complicated looking Smn theorem. It's quite complicated because all of the indices involved. You see the name for the reason for the name for the theorem. We have the function s. Is that the right way around with the m on the top and the n on the bottom? Yes, it is. So we have the Smn function here. So I'm going to try to explain what this means in two different ways, one of which I've already attempted, but I shall attempt the same explanation again, but in the context this time of giving the proof. So we're going to, again, it's going to be an outline proof. But the proof itself is one of these cases where thinking about what we need to prove actually helps us understand the theorem. So what we're saying is that there exists a primitive recursive function with a certain property. So we need to construct this function. So let's assume, given an n and an n, where n is strictly greater than n, and I'm going to assume that n is strictly greater than 0, because the case n equals 0 is actually trivial. You can think about that for yourself. Well, I mean, let me just tell you, in the case that n equals 0, the identity function on the natural numbers works here. So the case, so we don't need to worry about that case. So we'll deal with the case that n is greater than 0. So we need to show that there exists a certain Smn function and it's primitive recursive. So I already need my notes. I'm just simply going to define the function. I need to say what the function Smn does. We give it an index e, which we think of as an index for an n argument partial computable function. And we give it input values x1 through to xn. We need to return a number as the result. It's going to be a total function because it's primitive recursive. So what do we want to do? Well, we want it to satisfy this equality. So we want the number we return to be the index for an n minus m argument function, which when given the arguments xn plus 1 through to xn, computes the eth n argument partial function, the e index n argument partial function on x1 through to xn. So actually, it's not that hard to do that, because in the case that the number e we're given as an argument is the numerical code for a Turing machine M, then, well, the number E is the Turing machine, is the code for a Turing machine M that will compute the partial function phi sub E when given arguments x1 through to xn. We want to return the code for a Turing machine that takes n minus m arguments and computes that function when just given the last n minus m of the arguments. So what we do is we're going to return the code for another Turing machine, m prime, which is going to compute this function. And given a Turing machine that computes this sort of more general function with more arguments, we can convert it into one that computes this function by simply writing x1 up to xm on the input tape in front of the arguments xm plus 1 to xn given to the Turing machine m prime, and then behaving like the Turing machine m. So we simply, so where m prime is the Turing machine that begins execution by writing these m arguments to the left. So we want this to be a Turing machine that's going to take the remaining arguments from m plus 1 up to n. So we simply need to write these m arguments to the left of those, and then we'll proceed as the Turing machine m. So we write bin x1, comma, bin x2, comma, dot, 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 all the way up to bin xm, and another comma, because the input to this Turing machine m prime is going to start with the binary representation of xm plus 1. We want to separate it from the binary representation of xm. So we write this to the left of its input, and then proceeds as the Turing machine. And otherwise, we can return an arbitrary value. For some reason, I return E. Don't remember. But it only really matters what you do when E is the encoding of the Turing machine. Yeah.
Can you move the camera, please?
Oh, yes, I'm sorry. So this function is clearly computable because we take a number, we look to see, we take a number, we look we look to see if the number E is the encoding of a Turing machine. If it is, we then make a new modified Turing machine that just writes something to the left of the input and proceeds as that Turing machine. And it's easy to see that that's a kind of computable manipulation on Turing machine to modify the Turing machine M to the Turing machine M prime, and that one can then manipulate a code for M and turn it into a code for the corresponding M prime. But this is clearly computable. This is clearly a total function and clearly computable. Why is it primitive recursive? Well, that takes quite a lot of work to establish, and I'm not going to do that work. But in today's exercise class, you're going to see the power of primitive recursion, and by the end of that, you will be able to appreciate that with primitive recursion, you can do lots of things. And basically, any amount of computation where you can a priori bound the length of the number of computation steps you're going to need, you can deal with using the primitive recursion pretty much. So I'm just going to say it can be shown to be primitive recursive. The sort of thing I don't ever really want to do myself, to show that's primitive recursive. We're not really going to even need that this function is primitive recursive for this class, just it seems important, it's a known fact that it is, and it's important maybe to state that known fact. Right, so I want to again give another way of looking at this in terms of representations. So again, this is for the benefit of people that like to see things from a more abstract point of view, and hopefully everyone will get some benefit from it. It's not going to take long. So from the viewpoint of representations, we're saying that a certain function on represented sets is computable. And this function is, I wrote this down here. So it's the function that takes a pair consisting of an n-argument computable partial recursive function and an n-tuple of arguments. So we're thinking of a function that is realized by this function SMN. Its first argument is a code for a computable partial function of n arguments. And its second, and then it's got an n-tuple of other inputs. And it takes this, it's a total function that takes this to a computable partial function of n minus m arguments. And the function, so this function is the function that takes an f and an x and an n tuple x1 through to xm and returns. So f is an n argument function. This is an n tuple of numbers. And it returns the n minus m argument function that takes n minus m arguments numbered from n plus 1 up to xn, and maps those to f applied to all the n arguments collectively together. Okay. So we give the f some of its inputs, m of them, and that leaves us with a remaining function. We fixed m of the inputs, and we still have a function in n minus m, the n minus m remaining inputs. And the fact that the SMN function is computable is saying that this function here, well, let's finish this. So the function, need to get to the mess. So the function is in the red square brackets here. So there should be a colon here because it's a function from this set to this set. And it's saying that this function is computable as a function of represented sets and has a primitive recursive realizer. Okay. Just to say again, for those of you with a more computer science background, if you know something about partial evaluation, then this amounts to essentially partial evaluation of the function E that has n arguments by fixing the first m arguments. If you don't know something, if you're in a computer science background and you don't know about partial evaluation, you can Google it. Then you will see, and then that will help you to understand the SMN theorem. Let me just write that down. I want a green, well, anyway, it's the orange and green. So CF, that means compare, it's an abbreviation for compare, partial evaluation. And this is particularly evaluation, this is particularly for Ishirama students. Those with a more computer science background. Right. So I want to do one more thing, and gradually, somehow the technicalities involved in stating the results have been sort of gradually building up, I think, during the course of the lecture. And the next result is going to be the culmination of these technicalities. So we're going to, the next result is the most technical at all of them all, and it's not going to have, moreover, I failed to find a good explanation of it in terms of representations. So whereas the other ones, it's sort of, the representations give a conceptual explanation of what we're doing. This next theorem, I don't think has a similar conceptual explanation. It's a very nice technical result. There's nothing wrong with doing something very technical at the end of this week, because next week we're going to have a break from most you'll at least maybe do a few put a few technicalities, hopefully nothing too frighteningly technical in your presentations, but next week's going to be more a sort of impressionistic thing. We see lots of models and everybody needs to work hard for 5 minutes, but hopefully the rest of it you can more or less enjoy. So it feels fitting to do a bit of hard work as the last thing we do before next week's relaxation, apart from the time of presenting yourself, but maybe you won't be so relaxed at that point, but you should be, because we're all amongst friends. I'm not going to be very critical. I think the point is to enjoy ourselves, so let's look forward to that, and certainly we'll hopefully enjoy ourselves more than we're going to enjoy the next half an hour. So, right, but it's not so bad. So, I think without further ado, let me just state it. So I've already mentioned Stephen Cole Kleene's name before, but everybody calls Kleene now. So we have Kleene's, so Kleene is basically responsible also for the SMN theorem, I think, but Anyway, a very important theorem he did was what's called his normal form theorem, the point of which is we've got these recipes for producing the computable partial functions, namely it's the smallest class of functions containing the basic functions closed under composition, primitive recursion, and this minimization operation. And the point of the normal form theorem is that, well, one of the points of it is that you only ever need to use minimization once, and only right at the end. So the whole of the power of computability can be wrapped up as a lot of primitive recursion followed by one application of minimization at the end. So this says there exists a unary, so that's a single argument, primitive recursive function u. So I'll just write prim rec function u. It's unary, so that's just a function from the natural numbers to itself, and it's total because it's primitive recursive. And of each arity of at least one, and n plus 2 arguments, so n plus 2 array primitive recursive function again. So prim rep function, let's write fun, t superscript n, which has n plus 2 arguments, such that for all e x1 through to xn, the eth indexed partial computable function of arity n applied to the arguments x1 to xn can be computed in a standard way. And this standard way is, well, this is a partial function, so again, we're asking it to be Kleene equal. So Kleene's normal form theorem involves his own equality. We apply the u function, which is called the result extraction function, to what we get from minimizing the function. So I'm going to write it like this, minimizing the function that takes z to tn of e applied to x1 through to xn and z. Remember, t superscript n is an n plus 2 argument function. Let's count the brackets, 1, 2, 3. This is an n plus 2 argument function, but the last argument is the argument we're minimizing. So this notation, I mean, I could have just written it t n of e x1 through to xn. That would be consistent with what we had last week. But I think it's more readable like this. This is saying the minimization is looking for the smallest value z such that tn e x1 through to xn z equals 0. Okay, and because tn is primitive recursive, it's total, so the other more complicated conditions like that all the strictly smaller values the function has to be defined, that all of that holds automatically because this is a total function. So any the e indexed partial computable function is just obtained by applying. We can get it always from this single, or these two primitive recursive functions, u and t, and a single minimization. So it looks a bit preposterous. So just to remark on two things that hold here. And because of this, what we're saying is that phi n of e of x1 of xn equals u of z, where z is the smallest number. I'm just rewriting this in words, the smallest number such that t superscript n of e x1 through to xn z equals 0 if such z exists. So I'm going to try to explain this to you by describing now informally how this works. And hopefully, however hard it is to get your head around all the symbols, and hopefully you can get something from the informal explanation. I mean, these are the kind of symbol, this is the sort of result one needs to stare at a few times before one gets it properly. So the idea of the following, the idea is the following. I'm not going to really write a proof. I think the notes have it more formally as a proof. The idea of this function t superscript n, so we do this n plus 2 arguments, and e at the beginning and the z at the top. The idea is that, so this is a primitive recursive function, so it's total. The idea is the following, that this is 0. We're searching for a value that is 0, such that it's 0. So we kind of want to find a value for it to be 0, and then if we find such a value z, then we're going to get our result of the value applied by the e-indexed n-arity primitive recursive function. So this is going to be 0 only in the following very special case. The idea is if E is the encoding of a Turing machine M, the numerical encoding of a Turing machine M, or some Turing machine M, and Z is an encoding. The number Z is going to play a very important role, and this is going to, what Z has to do is encode the whole sequence of configurations in the execution of the Turing machine M on the input x1, x1 through to xn, on the input tuple binary representation of x1 through to xn. So Z encodes the whole sequence of configurations of M in the execution, let's just say the configurations in the execution of M on the input binary of x1, comma, set all the way through to binary of x sub n.
Camera, please.
Oh, the camera again. Yeah, I think I'm really sorry about this. I seem to be getting more and more lax about. Okay, So Z, we run the Turing machine M on the input of the binary representation of the numbers x1 through to xn, and we want Z to encode the whole execution sequence all the way to a halting configuration. So, and the last configuration in the sequence is halt with the binary representation of some number y on the tape. And otherwise, we'll return some arbitrary number such as 1. So the point here is that we can decide this. If we're given an E, an x1, all the way through to xn and a z, then z gives us, then the point is z is saying, I am an encoding of the whole configuration sequence of the execution of the Turing machine E on x1 through to xn. Well, first we need to check that E really does represent a Turing machine. Then we simulate the Turing machine of E on the of E on the input sequence x1 through to xn, and we wait to see step by step. We look at the whole sequence of configurations from the start configuration to where we've got to, and we wait to see if we ever get one that's equal to z. But if we ever get sufficiently far into the execution that we start going above the number z, well, then we know that z can't represent the whole configuration sequence, because you code them in some sensible way that the more steps you use, the larger the number that's going to encode it. So the point is, we're given a target z here, so we know when to stop in our simulation. We either hit z with an execution sequence in which we check that we've finished in halt and that we've got a binary representation of a number on the tape, or we don't hit z, we go past it, or we stop in some other state, in which case we return 1. Okay? And you now, so the point is, we're given an E, and x1 through to xn. This minimization here is going to look for the smallest z such that this is 0. In fact, there's a unique z such that this is 0, which is just the execution sequence that results in a halt with the binary representation of a number on the tape. And all U is going to do is it's going to say, well, okay, if I find such a Z, let me look at the last configuration, find the binary number on the tape, and return the number that's on the tape. So it's extracting the result from the sequence of configurations. It extracts the result on the tape in the final configuration. So U of Z is defined to be the result, the number y such that halt in y is the final configuration in the configuration sequence encoded by Z, if such a y exists, and if not, well, it doesn't matter what we return. So for some reason in my notes I put the number 17. But I mean, I know the reason, which is I put the number 17 if I want to remind myself that it doesn't matter what the number returned is. So anyway, so let's return 17. So you can see, hopefully, I mean, it's not actually hard to see this is computable and a total function. It's also not hard to see that this is computable and a total function. once again, it is rather complicated to show that they're actually primitive recursive functions. And if they're, well, somehow the whole point of the theorem is that they're primitive recursive functions here. So good that Kleene has showed that for us. As I say, in the exercise class, I mean, you're going to get some experience of programming primitive recursive functions today. So you'll get some feeling for the potential power of primitive recursive functions. And I think from that, you will probably appreciate for yourselves that you would, I mean, for most people, you would be unlikely to really want to see more details of the proof that these functions are primitive recursive. Okay, well, it's 10 to 5, but that's the material I wanted to cover for today. If there are any more questions about the presentations next week, I'll stick around for 10 minutes and happy to answer questions. Otherwise, you're welcome to go have an early break and enjoy the exercise class.